Okay, so I'm going to give you a couple more sections very quickly that we didn't get through in the beginning. We talked, and then we get to the lab. We talked about the key and query matrix, but we never mentioned the value matrix. So the value matrix is also one that comes in after. And basically what happens is this one's going to be a lot more abstract. So it's not as concrete as what we had for the key query matrices. But basically you use an original embedding for moving words around, right? However, that's not the optimal embedding we use the key query matrices for that, but that's not the optimal embedding for the LLM itself, for talking, right? Like we need another embedding that is optimized for the next word, where the next words are close by. It's not words being similar, but it's words being likely to be the next one. So it's, as I said, it's a little more abstract. But obviously, we can always go back to, and we can sort of find the similarities there and do the movement in the better embedding. I can be more concrete than that, going back to Taylor Swift, of course. Let's say this embedding has a lot of descriptions for Taylor Swift, right? And some of them are keys because they pull other words. Some of them are queries because they get pulled by other words. But that's not the ones that are used for talking, for coming up with the next word. And so let's say there's a bunch of other ones, could be some repeated, some could be keys, could be queries, could be none, that are actually good for coming up with the next word. For example, pop music, for example, Grammy winner, and let's say a combination of musician and artist. So there are some elements, some dimensions in the embedding that are actually the most useful and the most descriptive and the most predictive of the next word. So that's what the value matrix does. It just really focuses the word for the prediction of the next word. And that's the idea. If we see the value matrix as that, we pretty much understand what it is. Like, so key and queries help us find similarities between words. Value helps us predict the next word. That's all I wanted to say about value matrix. And now I'm going to tell you about positional encoding, which is the only piece in the puzzle that we have left. In this sort of, we pretty much went through everything, right? Softmax, feed-forward, attention. Well, we didn't go through feed-forward, but Annie's going to help us with that part of the whole architecture. Tokenization, embedding, and positional encoding. So positional encoding is interesting because nowhere in this architecture is the order of the words present. If I say a sentence and I say the same sentence, the order of the words all changed. Nowhere in this architecture have we addressed that. So positional encoding addresses that in the sloppiest possible way. I have to be honest. It doesn't really do something brilliant. It just does something, and then it just happens to work. So what is positional encoding does? Let's say I have the sentence, "No, it is good." Okay, that's a sentence. And then I have the sentence, "It is no good." It's the same words, but completely different meaning, right? It is no good and no, it is good. Completely different. The transformer sees them in the exact same way because when you put it in the embedding, they go in the same places. So we need to change this. And so we're going to just do one thing. The premise between positional encoding is this. I'm going to change the first word in a particular way, the second word in a particular way, the third word in a particular way, and then I always do the same changes, so the transformer kind of learns that and reverse engineers it. And as long as I give the transformer something easy to decode, we can kind of trust it. I know. It just sounds kind of magical. That's what it is. So for example, let's just say I'm going to move the first word towards the right, the second word up, third word to the left, and the fourth word down. And I'm going to do the same thing here. Notice that I'm changing things because no gets moved to the right, and here no gets moved to the left because it's in the third position. So I apply my moves. Now I'm changing things. And now I have a different embedding for each one of them. That's all we need, the fact that they're different. So now I don't have the same problem. I don't have the problem having the same thing. You see? And now the thing is this. As long as I give the model a predictable sequence like right, up, left, down, it can sort of figure it out and be like, oh, I think I kind of see what you're doing, so I'm going to reverse engineer it. Obviously, this is not good because it repeats, and then the fifth word gets sent to the same thing as the first one. So we can try something a little better, which is reducing the angle, right? The first word gets moved to the left. The second one, sorry, to the right. The second one in an angle. The third one in another angle, and so on. But unfortunately, we go back to the same problem because the 11th one gets sent to pretty much the same thing as the first one. So we've go back, as long as we have something cyclic, it's predictable for the computer, but it's, it goes back to where you started, and you don't want the 10th word to be sent to the same place as the first word. How do we fix that? Well, what we're going to do is we're going to change it a bit. So check this out. Let's say that I have an embedding of 6 entries, okay? So I'm going to take the first 2, then the second 2, and then the third 2. See, so if I only take the first 2, then the first 2, I'm going to do what I just did, okay? For the first 2, for the first word, I'm going to move them this way. For the second word, I'm going to rotate an angle, and so on. For the first 2, okay? Now, for the third and the fourth, I'm going to do the same thing, but I'm going to have a much smaller angle. You see? And for the fifth and the sixth, I'm going to have a way smaller angle. And so on and so forth. So if I have 1,000 entries in the embedding, I just take them by pairs, and then I disturb the first 2 by a lot, the second 2 by this much, and so on. And the 1,998 barely moved. So this is much harder to be cyclic, but it's still very predictable. That's what it does. And the formulas here, if you take a look, it's a little arbitrary. There's 10,000 to the blah, blah. This means you're getting smaller and smaller, so these are not changing. So it's all you want is a predictable, not cyclic, but cyclic-looking formula for the transformer to sort of figure out and reverse engineer, and then it has the information of the embedding and also the information of the positions. And so I've seen this, have you seen this picture for like positional encoding? I see some heads nodding. This is what describes positional encoding, and basically here are the things, right? Like if I look at these columns, things change a lot, because this thing is changing a lot. And as you go further, things get more and more static, because here they barely change. Okay, so this is a representation of how you change things around positional encoding. But basically the moral is, if you change the first word in a way, the second word in a way, the third word in a way, and you make that a sequence that's easy for the computer to understand, you have positional encoding. That's pretty much it. I wish it was something more clever than that, but it takes a lot of trust on the transformer. I think that's all I'm going to talk. That finishes the architecture of transformers. We have some links here that we'll put later, but Annie's going to, where's Annie? Oh, Annie's going to finish off with the transformer architecture, and then we really wrap up the whole transformer architecture, right? Amazing job.
Okay, so I will ask all of us to try and get this link, especially the middle one. So if you're doing the tutorial in English, so just put that in and it will direct you to a Colab where the tutorial is. If you want to follow, we also have a French notebook. So French translation of the English notebook, just put that URL. And we're going to get things started off. So we're just going to leave this here for a minute as we switch. I hope most people have taken a photo. And our helpers are going to walk around right now, and we would request at least one table, please have a running example that you could share. Like if you could get a running example in a notebook, that would be great. But please put up your hand if you're not able to connect, and we'll send someone there. Yep.
So everyone here, can I get a show of hands? Okay. So I'm already connected to GPU, but I wanted to show this. If I click on this, the first thing that happens is that I get into this link, and if my internet is okay, then you can see the demo. But otherwise, you can go to this site and try to connect to some GPU. I'm already connected to T4 GPU, if you're able to. Okay, and maybe what you can also do is to try to run all, because some of it takes some time, but we will walk through the notebook and I only have 5 minutes, so I'm going to try to keep the time. Okay, so the first thing we wanted to show is a demo of what you can do with a large language model, right? And when you go to the first one here, and let's see if we can quickly scroll through it. Just make sure you run all of the upper functions and yes, loading a model locally. So we're using Hugging Face. How many of us know Hugging Face? You've worked with it, you are working with, okay. It's a fantastic hub where you can download pre-trained large language model, and pretty much it helps you kickstart your LLM career pretty fast, quick. So get familiar with it. We're using Hugging Face, and once we also have this like very simple print sample where it tells you which model we are currently testing, and the prompt and the generated text. Yeah, let's do some demo. We're going to first start with, say, GPT-2. GPT-2 is a it used to be a large language model, but the scale of LLMs now is probably a small language model. Yeah, so it's about 117, the smallest one here, million parameters, and you can get up to 355 million. So it's pretty lightweight. You can run it on Colab comfortably with the GPU that you have right now. And we're going to get it to do something. So, for example, if you come here, we have a bit of option here, which of different models, but GPT is quite small, so we will use that. And you can start with testing it, say, once upon a time in Magical Kigali. And getting the output, you'll get to see this generated text. So, once upon a time in a Magical Kigali, the evil spirit of the mummy, which appeared to be San, told the mummy that, honestly, we're not doing great justice to LLM with using GPT-2, but I encourage you to test larger models. You're going to be very surprised what it can spit out. And there are also more, there's like GPT-4, 5. What's the latest one these days? Anyone? 5, right? Yeah. So you can get it to do more interesting things. Let's see if we can do some demo if the internet allows. You know, Luis said that it's you're just generating one sample at a time, right? So let's see, when we say once, then let's look at the next word, a probability of next word, and I'm just going to run this, if it's run quickly. Okay. I guess my bad. I did not start running everything. So let's try this one that I've run everything, see if it works very quickly. I'm going to reduce this to once upon. And we'll do a demo. Yeah. Let's see how long it takes. Yeah, see? It's running pretty fast, not bad. Okay. Once upon a sudden, a light appeared on the face of a hero. His eyes were filled with a bright, warm glow. He looked up at the hero. Okay. Yeah. Yeah, you can see the whole point of this demo is for you to play around with it. If you're very new, it's very easy, low hanging fruit. You don't have to do any coding right now. Just like play around, change the different model, but be aware that when you go to bigger model, you may be, not able to run it. So also maybe save some internet for other people. Okay, so the question here, the discussion that we would like you to have, and I'll pause for like 1 minute, is that what do you think the generated text, why do you think it changes all the time, even with the same prompt?
I just want to attempt, because in the first lecture, there was an insight towards this that reflects the lecturer mentioned the probabilistic option that make it changing over time. So I think that's what's responsible for it.
Yeah, yeah. So it's because of the probabilistic nature, but as we're sampling from a probabilistic distribution, and there are different ways in which you can sample. And one of the things that control that is the temperature. When you have a very low temperature, you're more conservative, predictive, but when you increase the temperature, it becomes quite creative. So I am going to allow you to play with these temperatures and give you 5 minutes after I finish running through this demo to just like play around with things. Another application that we have right here would be like code generation. To be honest, like GPT-2 is not the best for this. It's not trained, fine-tuned to do this kind of job, but it's low enough, but it's still able to tell you something. But this is not, correct. If you look at it very, very well, you would see that there's probably some problem there. And so you can also do a question answering where you ask it the question, and then GPT-2 try to just continue next word generation. It's not fine-tuned for that, but there is a model that is fine-tuned for such questions. So this vision question answering section, I'm uploading a picture from Wikipedia and I'm asking it, so what's in this picture? And you can see, this is the picture. What do you see in this picture? What do you see? Oh, yeah. Okay, so when we ask blip VQ base, and that tells you that, there are flamingos there. It doesn't tell you there's water or anything, but flamingos are in this picture. So kind of, in the same frame of mind. And you can also test out the chatbot using the Gemma models. You can talk to it to say, share one metaphor linking shadow and laughter. And this is a much more powerful model, so you can see that it's actually quite interesting to read, and it can continue the conversation. So it has, like you can have like multi-turn. All right, so that's my quick run through. We're gonna leave like 2 minutes for you to try it out, and I'll invite my colleague to continue when we have that. All right.
Cool, perfect. Let's appreciate Teju. Quick round of applause for that quick intro. So up to now, you have probably seen what LLMs can do, the different stuff, generate code. You've probably done a lot of this through like interacting with ChatGPT. But what we've shown you here is how you can easily load a model from Hugging Face, an open source model, and easily prompt it locally in this case, and not using an API interface. But right now, I just want to do a quick health check with regards to how many people are able to load the Colab notebook. Like, you're able to at least go through it, right? How many people are able to connect to the GPU, and you're able to run the cells? Great, so you're able to get outputs and stuff. How many people are able to run the cells? Perfect, superb. Yeah, so right next, I'll invite Ani, who will basically give us a quick recap of the full architecture and how it's going to be implemented in code. And I think from there on, we'll get ready to get our hands more dirty now with not only running inference on the models, but actually seeing how the different pieces come in together. So help me welcome Ani with a round of applause. Thank you.
Hi, guys. Thank you so much, Jabez. So before we look deeper into each section of the transformer, we thought maybe we'd introduce you to this quintessential picture that you might see in papers or in blog posts and go through it one by one. And what we will do in later sections of this practical is actually try to code and look deeper into how these different parts of the transformer work. So a quick bird's eye view of what a transformer model is, that it really is just a machine learning, like a neural network that is trying to predict the probability of the next token. That's a decoder transformer model. So you give it a prompt like wonderful day in Kigali or something, and you want to predict what the next token is going to be like. So then that makes this, this output part quite clear, yeah? So the input to the model is a sequence of tokens. So remember, Luis talked about words, but towards the end he said actually the input is tokens, and we looked at byte pair encoding. So you enter a sequence of words like I feel like eating, so like a few words, and then you want the model to predict a token forward. So the first thing that the models do is tokenize, so which is that they convert the words into smaller units, which could be less than words. So that's what byte pair encoding was. So remember byte pair encoding, which we will look into as well, breaks down words into smaller tokens. So even if you get an unknown word that didn't exist in your vocabulary, maybe somebody misspelled a word, or maybe you're a social media platform and there's a new hashtag, or there's a new, word that the youngsters came up with. Now that word is not going to be in your vocabulary, and that means that that word is going to get an unknown token. You're not going to have any information about it. So to prevent having a lot of unknown tokens, you can we use something called subword tokenization, which is like we try to divide that word into even smaller tokens and see, do we know the small part of this token at least? So in the example that Luis gave, you had ed. So if ed is at the end of a word, that means it's in the past tense, right? So we looked at the strange word besiegt, and even though the first part doesn't make any sense, we can still kind of infer that this word, this unknown word, is something in a past tense. So that's what's happening before, as soon as you input into the language model. So it's converting your words into tokens. After the tokens, they get converted into embeddings. So because we understand that neural networks need numbers to process, right? They can't really understand Arabic or any other languages. So they understand numbers. So we need to convert these tokens into some meaningful representation. And that was the session on embeddings, right? So embeddings need to denote words, but they are made in such a way that similar words are together. So that's, there's a famous saying called, you know a word by the company it keeps. So that's what happens in embeddings. That's the rule of how we make embeddings. Words that occur together need to be together in the embedding space. So once you have the embeddings, one of the things that Luis just again mentioned to us is positional encodings. So an input to the model could be a sentence, but I am happy and not sad, and I am not sad happy, has the same words, but in different orders, and it's opposite meaning, right? So we need to add some information to the input to this attention layer that tells the model what is the sequence of these tokens that I'm entering, and that's what positional encoding is. All of this then goes into these attention heads, and attention is really, if you were to boil it down, just trying to give you a weight for each word in the sentence, right? So like the common sentence, the cat sat on a mat, you probably don't need to put a lot of time, the model doesn't need to spend a lot of time processing the word the and right? What if it tries to spend more time processing cat and mat and things like that, right? So it needs to, it needs to give some weight or some score to these different tokens in accordance to how important they are to predict the next word. And that's all attention matrix is doing. You have some bells and whistles to the attention part, which is this add a norm, which we will cover as well today, but really just the summary of this add a norm is that one is the normalization. So you will see this in other architectures as well, like convolution networks or in other networks, that when you have a really deep network with a lot of layers stacked together, it's sometimes hard to optimize. It's hard for the gradients to flow. To stabilize the training, after each layer, we normalize it and make sure that all the layers follow unit variance. So that's all what normalization is. You look at the formula as well, and you'll be quite familiar with it. And then there's this add part. And essentially, this add part is also a relic of when you have really long networks, how to train them better. And the way to do that is you add the output of the previous layer, and you sort of bypass it and add it to the next layer. So the input to any layer is the input to the previous layer plus the output from that layer. Again, this is just used for more stabilized training. And then you have feed-forward network, network at the end of this, you know, these weights or this attention information that you got from each block. And that's really the neural network that you are quite familiar with or covered yesterday in the machine learning module, right? So it's just a feed forward, it's like a multi-layer perceptron with a lot of neurons. There's some nonlinearity attached to it, and that's the neural network that we're quite familiar with. If we didn't have these attention layers and we just put the embeddings and fit a neural network to it, we will not know which words matter more, or that not means that the context is the opposite of what is given in a sentence. So attention helps us weigh different words, and it helps us keep the context of different things that occurred, of different tokens into account. So attention sort of helps us process what is occurring in a sentence, and then we send it to feed-forward network, which processes it. And you can have a bunch of these sort of transformer blocks stacked together so that they continually loop through their understanding. So maybe at the start, like the first block is really just looking at the structure or the grammar of the sentence. And then when you stack a bunch of these together, they look at more long-distance context that has occurred. And really at the end, you have the softmax that gives you probabilities. So the softmax is the length of the vocabulary. So you're trying to get a probability for every single word in your vocabulary. And hopefully, the words that matter the most are going to have higher vocabulary. So that's really just what a transformer is. We're going to go through all of these sections one by one, starting with tokenization. So you can train your own tokenizers, like using byte pair encoding, but it takes a lot of time. So we're using Gemma's tokenization. So we're going to import their tokenizer, the new Gemma 3 model. We also highly recommend going through this this tick tokenizer, which is trained by OpenAI for GPT-2, and it kind of shows you how it processes different words. And here already you will see that in Daba, for example, one word, which probably wasn't in the training data for the model, gets broken into 2 subwords. So glad to be at Indaba gets tokenized into this. So one thing for you to do is maybe to try to encode a sentence in your own language and see how Gemma does for that. Gemma, will probably be able to get a lot out, but you can also do an exercise in doing using different tokenizers as well. So the idea here is try to tokenize using Gemma 3 in your own language and see how many tokens you get. Maybe try a well-known word, a sentence with maybe a well-known word, and then try something in English. So one of the things you will notice when you try to tokenize is that you'll see that English words generally get tokenized into their own word. So each word will probably have its own token. So if you see here, known English words will get their own token. Something you might notice with low resource languages or languages that are not very common is that the tokenizer will try to divide it all the way back into characters or like a bunch of characters, because it doesn't have the token for specific words in low resource or less common languages. And this is an open problem in natural language processing, because one of the sections at the end of this notebook that we really encourage you to go home and explore is that tokenizers are biased towards famous languages like English and French and German, so that when you enter a sentence, each word gets its own token. But when you enter a sentence in a low resource language, you end up getting many, many tokens, which makes the sentence very large. So the number of tokens is very large. And these models charge you per token to process. So it's a bit of an unfair design where if you are trying to do research in low resource languages or use it for your own use case, it might be more expensive to do. So in Ugandan language, they entered 2 words, 15 tokens came out. 3 words, 14 tokens. So you see, and try to enter 2 words in English. You'll get 2 tokens probably, maybe 3. So you see how unfair this is. It's because the tokenizer doesn't know that word. It never saw that word. It was never trained. Gemma wasn't trained on this language. It doesn't know these words. So what it is doing, so remember byte pair encoding? What's the first step of byte pair encoding? Convert everything into characters. Yeah? So it's going back and converting everything to one single character. And it's just saying, okay, well, I don't know this word, but I know its individual parts. So it's just spelling it out in that language. So that's what's happening. So that's great. All right, so that was, we got to move on to embedding. So now we understand what tokenization does, yeah? It converts everything to these individual units which get their own index. And then we move on to embeddings, right? So embeddings is this rich numerical representation of all of these tokens into this large space. One of the things about embeddings is that the larger the embedding size, the more nuance you can encode, the more meaning you can encode into the word. So maybe one of the embedding dimensions is talking about the tense of the word. So whether it's past tense, whether it's present tense. Maybe another dimension is encoding whether this thing is a food or not. Maybe another dimension, like Luis mentioned, is encoding whether this is physics or maths. Another one about gender, another one about grammar, another one about its technological advances, right? So for example, the word blueberry, right, can be you know, a fruit, but it also has a dimension of, BlackBerry has a dimension of being like a phone. Same with Apple, right? So it'll be close to words like banana, but it will also be closer to words like Google, right? So you need this embedding space to like make it close. So you need a large embedding space to make it closer to words like banana, but also closer to the words apple, while making, like Google, while also making sure that Google is not close to banana. You know what I mean? So that's why the larger the embedding space, the more of these richer contexts it can capture. So that's what's happening here, right? So these are my tokens. They get converted into token IDs. And then for each token, I have an embedding or this rich meaning and representation. So if I were to take like embeddings from this one model called Word2Vec, so this was one of the earlier models before like LLMs were in place that was used to learn embedding. And this model has like 512 embeddings. So that's the dimension size of the embeddings. Now human beings, we cannot really see more than 2 or 3 dimensions. So one of the things we've done is just use PCA, which is like a dimensionality reduction technique, which makes these 512 dimension embeddings into 2 dimensions so that we can see it. So if I was to show you how the Word2Vec embeddings look like, you can see this in your notebooks as well. So you can see that the 2 dimensions put the fruits close to each other, they put royalty close to each other, and then they put some like unrelated words like a little farther apart. And that kind of tells you what a good embedding is, right? So a good embedding is the one, like we said, puts words that have similar contexts close together. Okay, another thing that we do when we get embeddings is to add positional encodings, which is what we talked about, where we add the position of that token in the sentence. So this is the image that Luis also showed you, right? So here, essentially, in the earlier transformers, it was done by this very simple formula, where this POS denotes the position of the token. So is it the first token and the second token, the third? And then I is really just the embedding dimension. So for each token, you add this very simple, you know, these numbers to its embeddings, which are very easy to learn. So the model very quickly learns what this formula is, and this formula helps the model understand what is the position of this word in the entire sentence that was given to me. Here are some group activities that you can do, but maybe we can just look at the first one. So essentially the answer to this is really just that what Luis was trying to explain with the circles, right? So the first embeddings get a lot of change, and you see like towards the end, based on the formula, you will barely get any change. But obviously, if you're embedding dimensionals longer, you'll see this pattern like fully formed. But the idea about positional encodings, you'll never have to look at this formula really, is just to get the sequence or the order of words. We will now move on to more interesting parts of transformers, which is attention. All right, so now Amel will help us understand attention aspects of transformers. So let's give her a round of applause.
Okay. Great. Hi, everyone. Really glad to be here today. So basically, I will continue on what like Annie, Jabez, like Teju, and also Luis talking about since the morning, if we sort. Okay. So basically, yeah, as Annie said, like okay, 1 second. Okay, so basically right now we're going to talk really quickly about the embeddings they inform the attention. So the first thing is that what we did, we have like our text. From the text, we tokenize it. After the tokenization, we move it into an embedding. And from the embedding, we add positional encoding. And from the positional encoding, we feed it into the attention mechanism. That's the whole pipeline for now. How we do this is that basically we have like we learned the embedding, how they map and how they work, the tokenization with Annie also. So the first thing that we do is that we calculate the attention scores, which is the dot product of the query key on all the keys vectors in the space that we have. This will give us a pairwise similarity between the vectors. We introduced in the morning like the difference between the queries and the keys. And basically the idea is that you have from these like matrices, which are the query and the keys, we do as a dot product between them, and then we get another like output. And from it, what we do is we calculate the attention weights. We apply a softmax, and I'm sure like you understood why we apply the softmax and how it works with Luis in the morning. And then this will result in something called the context factor. Like just a quick historical overview. Like before with RNNs, the issue is that the context vector always have all the information from for example, the text. It was not in parallel. It was not trained in parallel, and this was it means that the context vector in RNN architectures before they were very, let's say, very dense and did not have all the information needed. In contrast, like the transformer architecture or the attention mechanisms help in this thing, which is basically we calculate the weights of the sum of the values vectors using the attention weights. So basically, after applying the softmax, we multiply it by the value functions. We will understand, like, we will have like later on a quick like analogy of the query keys and values. Okay, so right now, let's finally visualize the resulting attention like weights using the dot product attention here. As you can see, if you can like check it and finish these kind of scores, how would you try to implement this? Does anyone know? Like we have already know the formulation, so it should be straightforward. If you try to implement it, I will give you like 5 minutes for you to implement this function, which is basically calculate the scores, then you apply, you need to apply the softmax, and then after it, you need to multiply it with the hidden state. So basically, you have the hidden state, you multiply it by UN. Does anyone want to say how would you go through this? Like how would you implement the scores? How would you implement the WN?
Hi. We've been informed that QR code does not lead to the up-to-date version of the notebook, so I would kindly encourage you to go to GitHub, Deep Learning in Daba GitHub, and click on the collab from GitHub. Then it will lead you to the notebook that runs without any error.
So basically, all you have to do is going to the GitHub, Deep Learning in Daba 2025 GitHub, and then click on the practicals and follow the LLM practical, and then you can choose either the English or the French version as you like.
So if your collab says final draft, that's the wrong one. So if it says final draft, it should say intro to LLM. That's the correct one. So just come to GitHub, please, and I don't know how to get that QR code very quickly, but yeah.
So all you have to go is Deep Learning in Daba Practicals 2025. And then just go to the LLMs. Okay. Okay, cool. Yeah, please check the channel for the NLP. Okay, I think we can move on to the solution in this case, which is basically what you have to do is that to calculate the score, all you have to do is that you multiplicate the previous state with the hidden state transpose, and then you apply the softmax, and then you also, to calculate the context vector, all you have to do is just basically apply the matrix multiplication of the hidden state and the WN, which is basically the output of the softmax that we have. Okay, yeah, so basically if we take that, we have like words, for example, king, queens, royalty, food, apple, peer, and computers, for example, and then we calculate the word embeddings, which is using the word2vect, which is a very famous embedding like kind of model. And then what you apply is that you apply the dot product attention. What you get is you get the scores from these dot product attention. You get the weights, and then all you have to do is that you plot these weights of the different words compared to other words. So basically, if we can see in here, like what we have is we try to check, for example, the queen. Okay. The queen is towards the apple, for example, or here the king is toward the royalty, or food towards the computers. How are they related to each other? And we can see this using this kind of matrix, which is the attention matrix. And it shows, for example, here, like the queen is very related to the queen because it's the same word, right? And it's very close to the king, because it's very like the blue is very like dark in a way, so it's related to king. Food is not somehow related to the queen, for example, and this is how basically you can read this kind of like attention matrix. Okay, and then like we can see like which words have similar meanings based on this attention matrix, and yeah, you can have more information in this like blog post by Lilian Wang if you're interested. Okay, next we will go to the self-attention and the multi-head attention. Basically, the self-attention, we talked about it in the morning with Luis, which is basically like self-attention and multi-head attention are very fundamentals components of the transformer architecture. So we will go through how we are going to implement these using basically Python. So yeah, one second. So here, all you have to do is do an embedding sentence. Just run all through this, and then we will introduce, like we introduced before, like this formula, which is the attention, which is the softmax of the query multiplied by the key transpose divided by the scaling factor, and you multiply everything with the value function. So if for example, you have a sentence that a word, it starts with T, for example, the cat ate, like, I don't know, the mouse, it was very delicious to him or to it or something like that. Like the it, how it will refer to the exact like animal, which is either it can be mouse or cat. So we can through like, this is the whole idea, like how to attend. Self-attention is like you have different words and how each word attain to each other word in the sentence. And we calculate this using these kind of matrices, which is the query matrix and the key matrix. And then we multiply everything by the value. So the whole idea is that, for example, how are you doing in here? All you have to do is like, you have words, you took the token embeddings, and then you create like the weights the weights, which are the query key value matrices, which are, by the way, learned matrices. The model will learn them as he goes. And then you apply the formula that we have, and then at the end, you get the self-attention matrix at the end.
If you're still struggling to get to the correct notebook, that's not your fault. It's very confusing. Can I just show you? So if you're on the website, then the GitHub for the Indaba 2025 Pracs, confusingly, don't click on this blue link that says notebook, because that will end up in the wrong place. Click on this button, which says Open in Colab. But don't click on the notebook and then say Open in Colab, because that won't work. Just go to this README and click on Open in Colab, and that will take you to the right one.
Sure. Okay, just we need to go quickly for the, yeah. So basically here we calculate the sequence to query key value like matrix. All you have to do is we initialize the variance scaling of the different. Okay, cool. So we do the initialization. We have the query layer, the key and the value, and then we transform and return the matrices. And then in real life, what are the key query and values? I think Luis talked about it in the morning, but this is just a real life analogy. For example, imagine you're in a library trying to find the most relevant facts for a question. So the question in mind, that's your query, right? Each book in the library that has a title and a description in it, that's the key towards what you really want. And inside each book, that's the value, the actual value or the content that you need. So what we are trying actually to do is that we're trying to map the query and the value, the query and the key to the value, which is actually our actual content. And then in the self-attention, for example, the query is you're asking what am I looking for. The key is what information do I contain, and the value offers here's what can I contribute to the whole equation. So in general, self-attention is permutational invariant, and it requires no parameters, and is up to now the interaction between words has been driven by the embedding the positional encodings. So we expect values along the diagonal of the matrix that we saw, the matrix that we had, to be the highest. So the queen compared to the queen is the highest again. And if we don't want some position to interact with other positions in the whole sentence, all we have to do is set their values to minus negative. Yeah, I think that's basically the whole idea. There's also the scaling factor, which is the square root of the dimensions, that basically it ensures more stable gradient training during the training that you have. And then we have also the skill.product attention, yeah, which is basically this kind of matrix. Yeah, I think we can move to the next section with Jabez.
Let's appreciate Amel with a round of applause. Cool. So I'm going to spend a bit of time on this attention matrix. And to really quickly engage the audience and to see what you guys are learning from the attention. So what we basically did here is we had an input sentence written, I drink Coke, but eat steak. And we basically computed the attention matrix for this input sentence. And so intuitively what we did is we calculated the query key value vectors and their relationships, and then plotted the attention scores in this case, which are just probabilities between 0 and 1. Anyone wants to tell me why they think certain colors are darker than the others? Ignore the diagonals, but just look at different words. So on the x-axis is the same sentence, I drink Coke, but eat steak. And on the y-axis it's the same. Anyone wants to try this? What do you quickly see? Anyone jump? Yeah. Is someone here in front? Yeah. Go ahead. Okay, I'm gonna come here.
the similarities in the word and how would I put it, how it's been, how it's, the one word is dragging the other word, and how one word actually informs the other words, like drink, Coke and drink. Drink actually influences Coke, or Coke influences drink, and so it shows that they have a strong relationships and similar sort of, and then I and buts, and then the I can say, what's that again? Okay, hi and hi, fine, those are, they are the same words, so they are actually similar, like.
Great, perfect. Let's appreciate her with a round of applause. She got it right. So that's what Luis is explaining, asymmetry pull. So if you look at this heat map, you can be able to see drink, the drink on the y-axis has a high attention weight to the word Coke, because drink and Coke would likely occur together. And then if you look at the bottom left, eat and steak, you can be able to see the attention weights are higher. So that's the whole idea of attention. This is, visualize that. You want, within an input sentence, you want to compute the relationship between different tokens, and you want tokens that are similar to have higher attention matrices. So I'll move on to this next part a bit faster, just to like quickly go through the remaining part. So I'll really focus on understanding the intuition here. You can easily run the code on your own and get it right. So remember that during training, we're predicting one token after the other. So the cat is sat on the dash, try to predict mat. But during training, you don't want tokens to look ahead, because if tokens look ahead, what they're doing is that they're cheating during training. So what you want to do is you want to mask out such that at any given time step, at any given token, you only look at the back at the previous tokens during generation. So if you think about how decoder models will work, like ChatGPT, you would put in a prompt and then it would output one token after the other. In this case, you want to prevent it from peaking into the future. So what we do here is, in the original attention paper, after taking the query key values, applying matrix multiplication and scaling them, you have something we call a mask. And what the mask does is, if you run this matrix here, it has an interesting thing where it puts the ones on the diagonal, lower diagonal, and zeros on the upper diagonal. Anyone wants to give a shot at why they think we put ones on the lower diagonal and zeros on the upper side of the diagonal? Anyone? Is there anyone? Okay, so what basically happens is, if you look at this matrix that has been put here, this is an example of a mask. So we apply the mask to the attention matrix, and what this would basically do is, tokens are only allowed to attend to the previous tokens, not future tokens. So if you look at the upper diagonal, all of them are set to 0, and when you're computing the attention weight, they will have no impact. And so during training, you're not allowing few tokens to look at ahead, but you're just allowing them to look behind. And you basically apply a mask, and a mask is just simply defined as this jax.trill, and then you define ones, and then you define the dimension size, so 32 by 32, and that's the output you get. So that's the intuition I want you to take here. When playing masked attention, you just apply a matrix with diagonal ones that prevents looking ahead. That's the intuition there, right? So now we need to update our scaled product attention function to allow us to apply the mask. And what that happens is, in this line here, we just specifically say, if mask is passed, then apply our triangular matrix with ones. If not, we don't do anything. So that's the idea. So we finished with scale.product attention. So by now you've understood how to do it. But let's try to put this together into multi-head attention. So in a lot of training, you notice that one single head attention is not enough for training. You may want to get different sub-representation spaces to improve the information you're extracting. So think about this as like getting more juice out of the representations. So what we normally do here is you introduce multiple heads. So the same way Luis talked about query key values, just think about duplicating them n times, and then finally concatenating them with a brain. So that was what Luis was explaining, is that you split the heads into n number of heads, like 8, for example, and then you concatenate them by taking all their outputs and averaging them. So this diagram here clearly explains it. So you have your tokens that are represented from a sequence length, and each token gets mapped to multiple query key value vectors. You'll compute their scale.product attention separately, and then concatenate them through what we call a projection layer that lands this, and then you just get back the dimension of the embedding. So intuitively, think about multi-head attention as helping you to get more out of your representation subspace by having different heads focusing different things. And a lot of research has shown that different heads get to learn different features. So some heads are related with learning facts, some heads are correlated with certain linguistic features. So that's something important to note. So when it comes to the implementation, all you need to do is define the number of heads and define the dimension. So this is the dimension of the model embeddings. And in the setup function, so this is just a Flux module. It's just how you would set up a neural network module. And you'll define an initializer. And the initializer is just how to initialize your initial weights during training. And then finally, you have an output projection. And think about the output projection as the brain that takes all the input from all the heads and then just concatenates them based on some learned weights and gives you an output. And so if you look at this call function here, especially this part here, we basically take all the heads, the query heads, the key heads, and the value heads, and we duplicate them depending on the number of heads that we've passed. Now, something interesting that we do is the number of heads, just going back here, because in single head attention, the dimension can be quite big. Because we still want to maintain trainability, in most cases, you divide the dimensions of each head by, or demodel, take the original, and you divide it by a given value to allow you to have smaller query key value attentions. Yeah, and the rest is the same. You calculate your attention weights, you reshape that, and then your new model is the output projection, so WO with attention, and you return that. So that's the idea. So by now, you've understood three main things. So how to calculate self-attention, how to calculate masked attention, and also how to calculate multi-head attention. And multi-head attention is just simple in the sense that you take what Annie explained, Luis explained, and Amel explained, you just duplicate it n number of times, but then how you concatenate them is you train this guy called a brain, which is just a weight output projection that learns how to combine them. Okay, so lastly, we'll get to the last part, which is like, I guess, the fun part of you guys having to train. But Annie spent time explaining this, so I won't spend time explaining it. But this is an example of a feed-forward block. So intuitively, if you think about it, self-attention does not have any nonlinearity. So there is no way of learning like new things out of it. Hence, you introduce feed-forward networks. So in this case, you just define a feed-forward. In most cases, it's 2 layers. So this diagram here shows you the input layer and the output layer. So the input, you can think about it as output projection. So it takes in each token, and then it widens it. So the layer of a given MLP, the input layer is usually wide. And why we make it wide is because that's first easy to parallelize and train. And secondly, it just allows you to learn different features. And then you down project it back to the initial size of the model. And of course, you apply your favorite activation function. You guys know about this, LERU, GELU, SWIGLU, which just introduces some nonlinearity. So we do that. And then moving on to the normalization block that Annie talked about. So the add and normalization block, what it does is, after every sub-layer, you want to add back the original input, and this is the line here. So you take the original token, X, and add it to what you've learned. So the processed X is what has been passed through attention. And then you normalize it. And when normalizing, basically you're subtracting by the mean and the standard deviation. And the idea is that normalization helps to stabilize training, and that's important. And then finally, you just return it. So this is our final block where you have what's shown as block 1 is masked attention head, and then you apply normalization and addition, pass it through an MLP, which is the feed forward, and then add normalization again. And then that block is repeated a number of times, and you have your model there. Yeah, so quickly to show the decoder block, this is how we'd set it up. So first, you will define your number of heads, which you want. You define the dimension of the model, and then you define the widening factor, which is just takes in how to scale the MLP, so the feed forward. And how that looks like is you define multi-head attention, add normalization 1, the one after multi-head attention, and then add normalization 2, the one after the feed-forward neural networks, and then we define our MLP. So how a forward pass would look like is if we have a given input X, so think about this as a batch in sequences, we will calculate the attention weights by passing it through the multi-head attention. And then after that, we just add normalization, add X, which is the original input, plus the attention, what we've learned, and then normalize. We take that result, pass it through an MLP, and then we do the same thing, take the original input X, and add and normalize it, and we return it. So that's the whole block you have there. So finally, that's the decoder block. So when it comes to the LLM, it just contains multiple decoder blocks. So this code here shows you that you define the number of blocks, layers that you want. So this is how many times you should repeat the attention. And that just takes the decoder block and runs it n number of layers that you've defined. Remember the embedding guy that we defined? That's defined according to the vocabulary size. So it's a embedding of vocabulary size by dimension of the model. But I don't want to bore you with this. I will get to the good stuff. So here we'll define our hyperparameters. So this is stuff you may have seen yesterday, where you define the batch size. So this is how many instances you'll put. This is quite sensitive to the memory that you have. You'll define your sequence length, so how many sequences you should take. The embedding dimension is your dimension of the embeddings that you want to map to. And then the number of decoder layers is how many times you want to loop over the attention block, the decoder block, I mean. Yeah, and we'll run a sample example here. So if you look at this example, if we want to do a sanity check to ensure that our future tokens are not attending, current tokens are not attending to the future tokens, we just print this out. This is before training. So you can see, even without training, you can see that the current token only depends on itself and the previous tokens. Sometimes you run experiments and then you think you're performing extremely well, and then it turns out you were just peeking into the future. So if you're training, be quite careful. Sometimes you think that you're achieving quite good scores, but really it's because your code is looking into the future. Yeah, and then when it comes to training, we talked about this. All you need to do is we need to output a sentence. So for example, if you have a sentence that says, the cat is sat on the mat, it's very hard, intractable to predict the probability of that sentence alone. So what we do is we decompose it to the probability of each word. So in this case, the probability of the is like, you take the first word, the, and then the probability of producing cat is the probability of producing cat based on the previous token. And that can be decomposed into multiplication of the probabilities. So what this function here does is you take the probability of producing a sequence given a context is given by multiplying the probabilities for each given time step. And here P is parameterized by our model. So our model is the one that tells us the token to take. During training, what we do is we apply cross-entropy loss. And cross-entropy loss is just a way of comparing distributions. So we take what the model predicts and what we know is the ground truth, and we penalize if that distribution is not similar. And we average this across the sentence loss. If we do this a couple of times, the model learns through backpropagation and your favorite optimization approach. So you can run this, but I will quickly just get to the last parts that you see. So here we train an LLM using Shakespeare dataset. It's not quite as interesting, but I will just show some output. So an example of this output would be this text, like fast citizen. Before we proceed any further, hear me speak, all speak, speak. So this is an example of text. We'll basically train the model given this input to try and predict the target. And if you manage to successfully run the notebook, you should get this beautiful loss curve. Anyone wants to guess why it's decreasing? Quick guess as we finish. Why is the loss decreasing across training? I had it right, thank you. The model is learning, yes. I had it from myself. And yeah, we generate some random Shakespeare, and given a sentence like beginning with a prompt love, we can basically use our trained model to sample at each time step up to a maximum of 15. And even if you train this, you'd be able to see that it predicts love, he would meet again. Juliet, I tell thee, die wrong to you. So even if we've trained it, if you manage to train and run this notebook, this would train for about 5 minutes. You can already see that you're able to get a language model running on a Colab. Yeah, but that's the idea. In this naive example, we just took the top token. So if you look at this code here, we just take the argmarks, we take the top logit. But this is not efficient in most cases, so there are instances where you can use greedy decoding or beam search. So finally, yes, we are going to wrap up here. There's still more to come. I don't know if there are any questions. We'll take any questions, or Tej will help us wrap up.